To continue now, we have to Professor Roberto Capistrano introduce to Professor Alex Himonas. You can start, Roberto, please.
Okay, thank you, everyone. Thank you, Professor Alex, to accept our invitation. Well, today is a pleasure for me to introduce Professor Alex. I just give some few words about Professor Alex. Professor Alex received his BS from Patras University in Greece and his PhD from Purdue University. He's a current full professor of mathematics at the University of Notre Dame, where he has won the Canab Teaching Award and received a lot of National Science Foundation grants. Okay, his research interests include the regularity of solution to PDEs and Cauchy problems for nonlinear equation. Well, at least Professor Alex has at least 8 PhD students and around 100 publications in high levels between articles and books. Additionally, Professor Himonas has more than 2,000 citations of MathSciNet and more than 3,000 citations of Google School. Today, Professor Himonas gives us the pleasure of listening to his talk, Initial Boundary Value Problems for Evolution Equation and System via the Fokas method. Thank you again, Professor, for your time and for participating in our seminar.
Thank you for the invitation. It is it's a real honor for me to be included in this list of distinguished speakers, and I'm very happy to discuss mathematics with Brazil in person or via Zoom. So let's see. This is my title. You have seen the abstract. And I'm going to talk today about a work that we started thinking about this in 2008. I was on sabbatical. Professor Fokas invited me to Cambridge in the spring of 2008. And then he told me, you do initial value problems. Why you don't do also the initial boundary value problems? You do say the KDV on the whole line, and like applying using this Bourgain, Kenning, Ponce, Wenger methods, because they're in the initial value problem, using the Fourier transform, you solve the first linear problem, and then you use this to define your iteration map, and everything goes good. Now, for the initial boundary value problems, for the KDV on the half line, I'm giving you a similar formula. Why don't you use this formula and work like you work for the initial value problem? That was the question he asked me in I think it was March 2008. And I'm going to tell you what were the problems that took us so long time. So, but before going there, I'm going to tell you at that time what were the approaches used for studying the KDV and other dispersive equations on the half line or an interval. One was employing the Laplace transform, because since you are on the half line, so you can you can define Laplace transform on the half line, since you don't have full space. And then you solve the initial boundary value, the first initial boundary, the first linear problem, and go on. This was initiated by Bona and company, and also was employed by Erdogan and Girakis. Then it was the approach by Colliander, Kenning, Holmer, and others. I think there are lots of Brazilians. I don't know how many of you are attending this talk. I apologize if your name is not included, but you should know that if you look at my recent work, you will find your names there. So Yeah, and the third method is what Fokas asked me to do in 2008, but took me more than 10 years to start it. So let me, so that we don't have anyone complain, one of the big guys, say, give you some references about the approaches, the two first approaches. As I said in the papers you have written, you will see there is a comprehensive list of references, but here you see here the Bona, you see Colliandre, Kenning, Holmer, and lots of dots. I'm not gonna spend time in here. And then for the approach of Fokas, we are listing here some references for the initial value problem, starting with Bona, Bourgain, Kenning, Ponce-Venga, etc. So I myself was more wanted to do the ultimate goal is to do let's say the KDV on the half line, like Bourgain, Kenning, Ponce-Venga were doing the KDV on the full line. So these were the works that we were trying to see if we can use that method, the approach. And now I'm describing the third method that we call it the Fokas method. The Fokas method basically is to solve the first linear IBVP. Instead of applying the Fourier transform to solve it, because you don't have Fourier transform, we apply this method to solve this linear force problem on the half line. And the step 2 is using the Fokas solution formula, we call it, or UTM solution formula. Then do what Bourgain, Kenning, Ponce-Venga, and everybody does for the initial value problem. In other words, provide the linear estimates and bilinear estimates and all the rest. And the step 3 is using as an iteration map the Fokas solution formula when we replace the forcing with the nonlinearity and prove that it's a contraction in good spaces by also proving appropriate multilinear estimates. And the KDV would be bilinear. This is Fokas in his earlier years. Now he is 70. Last summer he celebrated his 70th birthday in Crete. In Crete, there is a nice volume that came from that conference. You could find it if you Google or if you see my papers. Something will appear there. This conference proceeding have already appeared. Okay, let's begin with a model case. By the way, this presentation is non-technical. I'm not going to give you the painful stuff for two reasons. First, I wanted more of you understand it, and second, this week is our fall break at Notre Dame, and I really do not want to work hard. So this is the model case, the KDV on the half line. This is the well-known KDV. Also, I'm not going to talk about physics like the previous speaker was talking. Today we are talking, let's say we are platonic. We are talking 100% math. We don't motivate it. So this is the KDV. And we have initial data given on the half line here. And we have boundary data given here on an interval 0t. So we want to solve it. And there are 3 steps that I described before. Step 1, in 2008, when I was at Cambridge, Fokas showed me this formula. It looks complicated. You see the first line is nothing. It's what you obtain when you do the initial value problem. But here, the only difference is when you see Fourier transform, this Fourier transform sign is not full Fourier transform, it's half-line Fourier transform. And then in the last line, you see This has to do with the initial datum, the initial data, and the forcing. The half line is about the boundary data. You see here the boundary data. And the boundary data, you see the formula is we degrade over the boundary of the domain D+. And the domain D+ is in the upper half plane, the Xi plane. And we have the midline, which if you look at the derivation, the way Fokas derived it, I'll show you some reference where you can find it. You can find also in our works when we do the well-posedness. This comes because when you derive it, you data that you don't know, boundary data you don't know, appear, and in order to eliminate using the symmetry of the KDV, you get this. You get this. You have, in order to remove the unknown data, you have to escape into the complex plane, the upper half plane, and also to integrate over this boundary. So here again, instead of in the first line here, when we have the transform here, spatial transform, this is like the line Fourier transform, but it's just on the half space from 0 to infinity. By the way, you can interrupt me at any moment. Don't wait till the end. So this is the half line Fourier transform, and this is time transform. At the end here you see the line transform, Z0. Let's see if we can get rid of this thing that hides the line for the time Fourier transform. Okay, yeah. So this is the time transform, and here this is the domain. And my problem was then when he gave me this, it didn't take me a long time to understand it. I derived it my own way, etc. But I sent, all these fancy techniques that they are used for the Cauchy problem. Typically, the integrations, we do Fourier analysis, estimates on the whole line. We don't know how to, I don't know how to do it on this. I had to estimate on this, on these rays in the complex plane. That was, call it the psychological problem I had, and had to take me and all my collaborators long time to understand. So here it is, if you want to see that solution of the first linear KDV and a linear Schrödinger and everything, here is the first paper where this method appears, and here is a book, the third reference here. You can see it. You can see details and many others. So what we showed earlier, this was the first step. Like in the whole line, we begin by solving the linear problem, and you get a solution that has only the first line. Now we have this more complicated formula that involves many lines, 3 lines, and also we have to deal with the complex plane. So the second is using this so-called complicated formula or difficult formula when you see it for the first time, we derive the linear estimates. Deriving the linear estimates here, of course, we start from if the data, the initial data are in HS, Sobolev space HS, between -3/2 and 3/2, and you have these compatibility conditions when you're above 1/2, where the Sobolev regularity gives you continuity. Then, if you estimate the solution to this linear problem, the solution is a function of the initial value, initial datum, boundary datum, and the forcing. So there, we get the natural, bounded by the natural norm of the data, the initial and the boundary data. In the correct norms, S + 1/3 is the time regularity known since earlier times. And then this is the interesting stuff. It took us a long time to get it. These are two norms. These are Bourget norms, spatial Bourget norms restricted to the time interval 0t. Here are the spatial in the spatial variable, and here is in the time variable. You're going to see this definition. The difficulty, one of the main difficulties here, it's the B, when you work on the whole line, the B is always bigger than 1/2. And Bourget did, when it did the periodic problems, B equal to 1/2 for the periodic problems. Here we have B smaller than 1/2, and this was a problem. Well, this is the latest work that I did, most of it with Fangqiyan. The earlier work, we were working in smooth spaces, above 1/2. Above 1/2, and in this, for example, we were getting the solution. The solution was bounded by the boundary data, like up here. But the forcing is in this angle norm. In this angle norm, it's difficult to prove contraction because when you put here the nonlinearity, and this problem was faced first by Koenig-Ponce-Vega in, I think, 1991, when they were trying to get solution to well-positions of the KDV using Sobolev techniques, not Bourget spaces, because Bourget spaces were not defined then. They were using the so-called famous, if you have ever seen that paper, lambda norms. It was a subset of the Handemart norm. So now here are the Bourget spaces, the Bourget solution spaces. This is a standard Bourget norm where we're on the whole line, and here we have this extra corrector. That's why I call it modified. And in fact, this was defined in the paper 93 of Bourget when the B was equal to 1/2. If B is bigger than 1/2, you don't need this blue part. But if it's 1/2 or lower, then you need it. And here are the temporal, because why do we need this? Because we see these spaces into the linear estimates. These come naturally, always. You do your best to do the linear estimates, and then you see these norms appear in the forcing. If they appear in the forcing, then they will appear in your own linearities, and you have to do things. Here it is really is when you replace the spatial derivative with the time derivative, and we know the time derivative is 3 spatial derivatives. So instead of 2s, you will have 2s over 3. So this is the temporal Bourget space. And by the way, I don't know if you noticed it there, let me go back. This, you will find it in Faminsky. And after that, many other people, in particular the group of Koenig-Ponce-Vega, Linares, etc., they have been using this. And many of you down there in Brazil. So now we have to prove, because this appear in the linear estimates, we need bilinear estimates in the spatial Bourget spaces, modified Bourget spaces, and here are the bilinear estimates, which is like the estimates on the whole line. Critical minus 3/4, and here also you have the temporal estimates. Again, critical minus 3/4, and there are so many parameters here. I would not recommend you to try and understand. Just seeing these two inequalities, bilinear estimates, sound familiar if you are in this business. And then you need all this in order to do big data and everything. So we were able to prove these bilinear estimates. And once you have the bilinear estimates, then you go in the iteration map, the Fokas iteration map, replace the forcing with a nonlinearity, and then you do the standard arguments, and you prove well-posedness. Here is again minus 3/4 up to 3/2, and we avoid to skip s equal to 1/2 because there are some extension problems there. And then what do? We find solution, which solution belongs to the spatial, to the modified spatial Burgerian space restricted to the interval 0 T0. T0 it's the lifespan. It's the lifespan, and it is 1 over this power. This 4 over b is positive. B comes out of the bilinear estimates. So the bigger the data, the smaller the lifespan. And you have also the solution size is bounded by the data size. And the solution is continuous. Actually, it's better than solution is unique and better than continuous. In fact, it's Lipschitz continuous. And this is the KDV. This is what we wanted. This is 2008. This is I wanted to prove this theorem. But this is a very recent result. I will show you later. In 2016, in the nonlinearity, we did it up to 1/2. Below 1/2, using the more or less ideas with the lambda norms, the Kenning-Ponseveng 1991 paper. And because you had this Anglian norm, when we were putting the forcing in this Anglian norm. And now let's, in order to test myself and collaborators the power of this method, now the new method, the third method, we tried some curiosity equation. This is, we introduced it with a PhD student of mine, I think, goes to early 2000, I think, 2009, it's a paper, and others worked on this. So here we have a higher dispersion KDV. Here, if you put m is equal to 3 or m is equal to j plus 1, if you put j is equal to 1, then you get the KDV here. For m is equal to 3, you get KDV. For m equal to 5, you get the Kawahara equation. We have just one initial data, and we have many boundary data. How many? As many as j. We have j boundary data, and this is the problem. I don't know if following the Bona and Dole approach or the Kenning and collaborators approach, I will be curious what the Kenning crown in Brazil, if they try that, if they can get it. However, here, if you are willing to work, be patient and work like a good calculus student at Notre Dame, work for a few months, you're going to get this beautiful formula. Again, the first line. By the way, the initial value problem for this equation started 2009, and we got the best result with Fang Chi Yan and Renata Figueira. We got it in not long ago, just I think 2020, something like that. And by applying the standard method on the line. But here we have this 3-line formula, which is more complicated as expected, but just it's not difficult. Computationally is challenging, and instead of having now one domain, one in the upper plane, you have here j domains, and there are in this beautiful thing, and then you have this formula. And let me show you the transform. The transform is the same on the half line, and the f, it is the mixed time and Fourier transform, the usual thing you get in the initial value problem. The life, the time transform about the same. And of course, the Burgerian, the spatial, modified Burgerian space, spatial and temporal. The only thing is the symbol is different. So instead of xc to the cube here, you put xc to the m. And in the step 2, now we could do the linear estimates, and you get again, this is time regularity. the solution now with J data and the forcing, initial data, 1, J boundary data and forcing. In this Bourgain space, it's bounded by the natural norms of the initial data, time regularities of the boundary data. These are, no matter what method you are going to use, you are going to get them. And then you have the two Bourgain spaces. This is the Bourgain space, the spatial Bourgain space, and here the temporal Bourgain space. And here B, again, is smaller than 1/2. And alpha, that helps, is bigger than 1/2. And here are the, I'm sorry. I don't remember if I have these spaces. Yeah, the spaces are here. We gave you the spaces earlier. And here are the bilinear estimates. We have bilinear estimates like that. And by the way, we got this sharp estimate, this sharp using our methods. Bilinear estimates, you go to minus J plus 1/4. If you put J equal to 1, you get minus 3/4. This is the first bilinear estimate. And this is a temporal bilinear estimate. Here, the ones that one would expect to get in analogy of the initial value problem. So then, if you go to the Fokas solution formula that defines the iteration map when you replace the forcing with a nonlinearity, and you do the standard arguments, and you put there you applying the bilinear estimates, we're going to get here Wolposnes. The solution will exist into this modifying Bourgain space with this bound on the size of the solution. This is the natural bound, the bound of the data, and here the lifespan. And again, the solution is unique, and the continuity is Lipschitz. Okay, so this really convinced at least me that from all methods you have right now, at least in one dimension, this is the most general, this Fokas method, starting with the Fokas method, but afterwards you get into, because it gets you into the standard classical material. Of course, there are difficulties because you have to do some analysis on these rays. Okay, after we finish this, by the way, this KDV system, it is a JD 2022. If you want, all these papers are published, and we have here the bad habit of providing details. And there are these papers are written in detail, and there is lots of references. And most likely, if you work in this area, you're going to find your name there. If you don't, please send me an email to include you in the next paper. And here is about systems. And here I'm going to talk to you about the MKDV system. I'm sorry again, some of the names. Marcio, I think you worked on this system or some system of this nature. Your name is not here. I apologize. It's not because I thought you would not be in the audience. I decided to keep it clean. Here we have the MKDV system, and the MKDV system. We have here the cubic nonlinearities that are symmetric. But here we have an alpha parameter, and the alpha is bigger than 0. And here the initial data, and here the boundary data. The only difference is this is two coupled MKDV equations, and here are the initial data, and here are the boundary data. And by the way, I don't know if there is any physical physical application, or if it comes from a physical system, but we will land there in terms of motivation with, you can see it for the mind-Nebbiolo system. I'll show you the mind-Nebbiolo system, I think, next, after I finish this. For this MKDV system, here is the theorem, and we know for the well positions of the KDV on the line is 1/4. Here we work for rough data. Of course, you can go above 3/2, then you're going to have more compatibility conditions. This is a paper that just appeared. This is in the journal 2023, and we have well positions for S bigger than 1/4, and above 1/2 we need these compatibility conditions, and the natural space for the boundary data, etc. And here are the usual spaces, the Bourgain space, the Bourgain space here, and the restricted Bourgain space here. So this alpha now, this is not the previous alpha we had in the modified Bourgain spaces. This alpha comes from this parameter. This is the parameter. Unfortunately, the letter alpha is everywhere. Okay, this is the mind-Nebbiolo system. The mind-Nebbiolo system, mind and Bielo, they derived it from some waves formed up in the atmosphere. I'm not gonna go into it, but it comes there, and it seems, at least the way they derive it, is in a periodic setting. This mind-Nebbiolo system, and this also we have done this, and it just appeared in the nonlinear analysis 2023, and this is a very, very curious phenomenon, which in the case of the mind-Nebbiolo system, here I'm giving you the critical exponent. You see, the critical exponent, well, Poisson's exponent, depends on alpha. And my explanation, our explanation, is because the nonlinearities are not symmetric. But you may have other explanations. So the theorem here says, if S is bigger than S critical alpha, as you see here, then this mind-Nebbiolo system is well posed on the half line. I'm not going to say more on this, but you can find it. And here it is a scaling that makes, we are going back now to the MKDV system, which in fact, instead of working from 0 to infinity alpha, you can restrict it from 0 to 1. This is the alpha. But again, I don't know how you feel about it. If you have any comments, let me know. In the MKDV system, the MKDV system, the well positions does not depend on alpha, and on the mind-Nebbiolo it depends on alpha. There are people that have done the initial value problem. I'm not going to go there. You can go in the references of our papers. Again, now it may become boring if I tell you this Fokas method. It's a kind of standard analogous to IVP. In the step one, you are going to solve the forced linear problem. Here there will be two. One is the linear problem with linear KDV with alpha equal to 1, and then the linear KDV with alpha coefficient here in the dispersion not to 1. And here the solutions look alike. Simply now you will see here we describe the solution here is this is the S1 for the first one. We have two solutions, two problems, and the other is for with the alpha. Actually, if you put in here alpha equal to 1, you get the first one. So we have the linear the solution to the linear problem, and here again the half-line Fourier transform and the time Fourier transform and the other mixed space-time quantity here. The quantities, they appear in the thing. And here is the theorem. The theorem about the linear estimates. In the linear estimates now, if we are, you can go at -3/2 because it doesn't see the nonlinearity. This is the linear estimates. You get it also for the KDV. This is the same linear estimate before. And here are the usual spaces you have seen before, the linear estimates. We have both the spatial and the temporal Boolean spaces. And now if, again, here we write the iteration map after some cutoff, you replace here the F1, the nonlinearity, the first nonlinearity with this forcing, and the second nonlinearity of the second equation with this forcing. And then you will see that you have to prove these bilinear estimates. And these bilinear estimates require lots of work, but there is lots of ideas. The only difficulty again here, it is because the b's are smaller than 1/2. For b bigger than 1/2, these have been done. And here we have, because again, we were worried about is it optimal, and it's optimal. Below 1/4, you don't have such bilinear estimates. And believe it or not, this is the last transparency. I don't know how I'm doing in terms of time. This is the last transparency. So what we did today, we saw, you can see, by the way, the KDV. We have not written the KDV in terms of the Dirichlet. We have done the KDV in the Neumann and the Robin-Neumann problem. But in terms of the Dirichlet, you're going to get it from the KDVM. Our 2020, if you want to see this method just for the KDV, all the details done, you go to the KDVM paper, JDE 2022, and you set m = 3. This is actually the breakthrough. That's the paper we were able to go from to the rough data. So we did the KDV, the KDVM, the NLS in 1D and in 2D. This is a work with Matzevinus. In 2D, we did both the Dirichlet and the Neumann problem. Then, in terms of the systems, you saw here, we did the Mind-Biolo system, although I didn't talk about it. We send the Mind-Biolo system, where portions depends on alpha. The MKDF system that we talked a little bit about it, where the well portions does not depend on alpha. And the SKDV system, which it's not included, but we have written a paper on this too. All this. And we have done also what I talked today, all of it is Dirichlet problems, but we have done all these things for the Neumann and for the Robin. So the conclusion is what we didn't know, what Fokas encouraged to work on this project, and he was saying he believes it will be, although he's not a PDE person, believes we can develop a theory analogous to the IVP, and we could say this is the case. And I don't want to undermine the previous two methods. We have to have all methods. I don't want to say if this method is better, but I believe this method is more general. And thank you for your attention. And again, there are not many papers here. This is Faminsky that I told you, the space that the new space. Oh, this is the paper. It was 2020, the KDV with higher dispersion and some more here. Thank you again.
Thank you, Professor Himonas. Thank you very much. Are there some questions, comments, or curiosities? Well, please, everyone can write the question in the chat or just stay in the microphone. Let me start very briefly. Professor, about the bounded domain.
Yes.
You have, of course, you prove most of the results in half line. You have the left hand side,
Yeah.
But I'm saying about the bounded domain, imagine 0L in the rectangle or something like that.
On the interval.
Yeah, in the interval.
Yes, on the interval, we have, I didn't, I don't know if I mentioned here on the interval, is there somewhere? Yeah, we have a paper on the interval for the KDV. I don't think we have written anything for the NLS, but the KDV on the interval, you will find the paper. If you look at MathSci, you're going to find one. In fact, this is Himonas, Manjavinas, Jan, this paper.
Oh, okay, but okay, more general, for example, for KDV, like the ABCD system, if you remove the BBM terms. KDV...
I told you, for example, the previous speaker, they introduced lots of equations. I just wanted also to tell you what we have done. And what we have done, you see it here.
Okay, perfect.
If you start, let's put it this way. KDV and NLS, we have understood it very well in one dimension, but we saw from the previous speaker lots of equations that, yes, there are lots of equations. In particular, when you have this non-local term, there were many of these Bushinesque type equations that have no local term. We are not, there is plenty of work. Okay.
Perfect. Okay. More questions, comments? Let me check here. If not, thank you, Professor Himonas, for stopping your break in the Notre Dame to give for us this very, very good talk. Thank you very much for your time. And well, hopefully see you in Brazil once.
Okay. Well, again, thank you very much for inviting me, and you too. If some of you have already visited Notre Dame, if you plan to come to Brazil, to leave Brazil and come to the US, let me know. We are not far from Chicago, from the Chicago airport. You can be at Notre Dame and only you can come. There is a plane that arrives, but we have also, there is a train. You get the train, and with $10–15, you can get from the airport to near campus 25 minutes from campus. Again, thank you very much, and nice seeing most of you.
Okay, thank you, Professor.
Okay. Bye.
Bye-bye.
Thank you, Roberto. Thank you, hello, Professor Alex Himonas, for your amazing talk.
Bye.
On